so far. So the very first type of rate law we learned was called the what? Which one? The differentiated rate law.
Yeah.
I heard a lot of things. I'm not sure if I heard that one. Okay, or you were drowned out by that.
I remember
okay.
it wasn't integrated.
Okay, it was differentiated rate law, but we said it's the most common one, and so it just gets nicknamed the rate law, right? So if it asks for what's the rate law, that means we're just looking at the differentiated rate law. So that's the one that's up here, right in the very top of your cheat sheet. R equals K times concentration of A to X, concentration of B to Y, okay? So that would be the regular rate law, which if you see up on our slide right here, would be this guy, right? This is assuming that we just have one reactant, okay? And when we use the differentiated rate law, we're talking about how the concentration affects the rate of the reaction, right? How concentration affects the rate of the reaction. But then we started moving into the integrated rate law. And integrated rate law shows us the relationship of the concentration over time, right? How does time affect the concentration of a reaction? So they're measuring two different things, right? The differential rate law or the rate law shows us how a change in initial concentration affects the rate of the reaction, right? That's where we look at what's the initial concentration and what's the rate. But the integrated rate law shows us what happens to the reaction over time, right? As time goes on, what happens to the concentration of the reactants and the concentration of the products, okay? So that's the difference between the two kind of genres of rate laws here, okay? We talked about first order rate laws in our previous class, and first order rate laws are distinguished by a graph that has what type of slope?
Negative.
A negative straight line slope, right? That gives us a negative straight line slope is a first order reaction, okay? And so that's really how we're going to start differentiating our integrated rate laws is by their graph and by their slope, okay? I did on your little cheat sheet there give you kind of an overview of what each of those types of graphs should look like, right? The first order integrated rate law is going to have this negative straight slope. Now, it might be a little steeper, it might be a little shallower, but it's going to be a straight line negative slope, okay? And when we're looking for a first order reaction, we'll get a negative straight line slope by graphing the natural log of our concentration, right? Not just our concentration, but our natural log of our concentration. So we've got to start making some connections between first order is always going to use the natural log because our integrated rate law first order equation includes the natural log in it, right? So we've got to start making some ties between first order and natural log, right? That's information that we're going to start putting together. So now let's look at a second order reaction. A second order reaction doesn't use the natural log anymore. It uses the inverse of our concentration, okay? 1 over the concentration of our reactant, right? 1 over. This is new, right? These are second order reactions. So today we're going to talk about second order and zero order. That will kind of wrap up our new types of material, and then we'll do a lot of practice with all three. Okay? So, doesn't this equation look the same as our first order equation? Doesn't it have the same base? Right? Y equals mx plus b. Right? We said they all relate to the equation of a line. Okay? So this is the same except in our other one we use natural log, right? In first order we use natural log. Here we're using the inverse of our concentration. What do we know about this A sub 0 right here? That's our concentration when? When time's at 0 or at the beginning of our reaction. And then this regular A concentration here is at whatever time we're plugging in for T right there. So if we're trying to find the rate constant at 15 seconds, we would plug in 15 seconds here for our time, and we'd plug in the concentration at 15 seconds, right? That would go right there, okay? And then this would be our initial concentration over here, okay? So equation's going to still mimic the equation of a straight line, mx plus b. Now the difference here is that our K rate constant is not negative, right? In the other one we had a negative KT because our slope was going to end up negative. But in a second order reaction, we actually see a positive sloped graph. Okay, so here is what our graph would look like when we just graph the first order. Okay, this graph over here would be a natural log. Okay, natural log. If it was a first order reaction, we would have seen a straight line here because it's natural log versus time. But it's not a first order reaction. It's actually a second order reaction because 1 over the concentration gave us a straight line. Do you see the difference? So I'm going to graph both of them and see which of them gives me the correct correlation. Okay, if I was graphing this one, natural log versus time, to confirm that it was a first order reaction, I think I would have to say, no, it's not, right? Because that's not a straight line with a negative slope. Would we agree? Mm-hmm. Right, this first graph right here is not a straight line with a negative slope. It's got a curve to it. And so then I'm going to have to take my data, find the inverse of my original concentrations, and graph them versus time to confirm to see if it is second order. And it does, right? It's a straight line. We know it's supposed to be a positively sloped straight line. So this would confirm to us that this reaction is second order. Okay, does that kind of make sense?
So we have to do the first, and then...
Well, kind of, right? If we're going to depend on what it gives us in the problem. Some problems tell us this is a second order reaction, right? And then we can work from there. But we're going to see problems later on where it just gives us concentration and time. And we're going to have to derive basically 3 different graphs, right? And so that's what I'm going to teach you how to do it in our calculator. Okay, so that will speed that process up just a little bit. Okay, but yes, essentially we would have to graph the natural log versus time, the inverse versus time, and the information for a zero order versus time to figure out what type of reaction it is. Because from that, we can then go find the rate law, and we can find the constant and things like that. So we've got to figure out what order it is first, and we usually do that by a graph. Okay, so again, in the second order reaction, here is your equation for the half-life of a second order reaction. Half-life of a second order reaction. K is our rate constant again. A sub O is our initial concentration. So we don't have any constant value like we did in the half-life of a first order, where it was that 0.693 over, right? That was a constant that we used. That's not the case for a second order reaction. Something I do want you to point out right here in a second order reaction is that the half-life gets longer as the reaction progresses and the concentration of reactants decrease. Each successive half-life is double the preceding one. So that's really important information. I want you to highlight or circle that or something, and I'm going to talk you through kind of what that means in just a second. Okay, before I hit on that part of the second order, I want you to add this here. Half-life of first order reactions does not change. So half-life of first order reactions, it doesn't change. So that means if my half-life is 30 seconds, right? If my half-life is 30 seconds of a first order reaction, to go from 1 molar to 0.5 molar, it takes me 30 seconds. Then to go from 0.5 molar to 0.25 molar, it would take me another 30 seconds. Then to go to 0.125 molar, it would take me another 30 seconds. Do you see how that works? Right? To cut my concentration in half, it takes me another 30 seconds. But for second order reactions, we will see our half-life increase, and it's double the preceding one. So let's look at that same kind of example here. So if I'm going to go from 1 molar to 0.5 molar, the first one might take me 30 seconds. Then to go to 0.25 molar, it might take me 60 seconds, right? Then to go to 0.125 molar, it would take me 120 seconds, right? Each half-life doubles. So it takes longer to finish that reaction. All right, does that kind of make sense? Our half-life changes for second order reactions. Okay? So let's look at this real quick. Did I hit zero order yet? No, I want to do this one first. Okay. For the reaction, some reaction A to products, right, means we only have one reactant. Our initial concentration is 5 molar. The first two half-lives are 25 minutes and 50 minutes. Write the rate law, calculate K, and calculate our concentration at 525 minutes. So it doesn't tell us, is it a first order or a second order reaction, but how can we determine that?
The half-life doubles.
The half-life changes, right? And specifically the half-life doubles. So if my half-life is doubling, that has to be a clue for us then that our reaction is second order. So if I want just the rate law, not the integrated rate law, just the rate law, I would say R equals K times the concentration of A to the what order? Yep, to the second order, right? That's the whole point. It's a second order reaction. I only have one reactant up here. Okay, I only have one reactant. Calculate K. All right, I've got my initial concentration and I've got my half-life. So can't I use my half-life equation to solve for my initial concentration? Go take a look back at what's my equation for half-life of a second order. 1 over K times what? My initial concentration. And so here is my 5 molar. Okay, I'm going to use my 25 minutes right there. Okay, and so I'm going to end up solving there for K. Right, I'm actually going to end up just switching these two spots to begin with. All right, I'm going to move that. So let's say K equals 1 over 25 times 5.
What if you use the 50 minutes? Would it change?
Yeah, because that's the second half-life. So it's not, it wouldn't give us our initial concentration there.
Okay.
And so I got a K value of 0.008. Go ahead and run that through and see if that's what you got as well. All right, I'm going to use the equation that says 1 over concentration of A equals KT plus 1 over concentration or initial concentration of A, right? That's our integrated rate law equation. So basically that cheat sheet I gave you is the set of equations for second order reactions that we can use. So you need to kind of mix and match to figure out how can I solve for that, right? But that's the information that you can have. So I'm going to do 1 over A, that's what I'm solving for, equals K. And I'm going to use 525 for my time, plus my initial concentration, so 1 over 5, right? If it was asking for our concentration at 50 minutes, I could go 2 half-lives, right, and be done with it. But 525 minutes is a long way for me to walk to figure out if that's a half-life, right? I'm just going to go ahead and plug it in. But if it's an easy one, even if it's at 100 minutes, you could say, okay, well, I know that's 3 half-life cycles, so I could walk from 5 to 2.5 to 1.25 and be done, right? But this one doesn't really follow that as well. So just be thinking about that as you go.
So would you just run
I'm going to run the math and just solve for that guy.
Oh, so but if we were doing it for 15 minutes.
Does anyone finish that or not quite?
Yeah.
4.4. I got 4.4.
You well, if that's your answer on the right side, you have to take it 1.
Yeah, very good.
1 over 4.4.
Which is the 23.
So where you're at right now is 1 over concentration of A equals 4.4. But I don't want that to be in the denominator, right? I want the final concentration of A, so I've got to take 1 divided by 4.4, and I get a final concentration of A equal to 0.227 molar. So you want to check to make sure your answer is rational, right? If my final concentration had come out greater than 5, what would that have told you? right? That's a problem because there's no way our concentration would have grown, right? So always check to make sure, does my answer make sense? Is it rational? All that good stuff. Okay?